Hello everyone. So in the previous class, we started the implementation of brain tumor image classification. Okay. There we have seen we are available with four classes. Okay. Three classes are of tumor and one class is no tumor. Okay. So that's multi classification problem. Fine. I explained you approach, what you have to follow in order to do the analysis of such kind of data because you are having image data. Okay. So what's the easy steps which I taught? The first thing is we have to convert the data into data frame. Okay, I made df as a data frame where I was having the path of the image and the category of the image. Okay, so I converted it into data frame. Then I performed the count plot and pie plot in order to show how many images are of particular category. So count plot and pie plot I made. Then I also plotted five five images of each category. Okay. Then I did performed random oversampling. Okay, and we had a good discussion in oversampling because the question asked to me, "Sir, you did the augmentation." I said, "Yeah, it's like increasing the number of images, but the duplicates were not specific." So we had a good discussion. Okay, and then the next few pre-processing steps were left, which we will cover soon. Okay, I also explained VGG16 architecture, and in this architecture I told we are having 13 convolution and 3 deep layers. Okay, fully connected layers. So 13 convolution and 3 fully connected, like, okay, deep layers. So we are mentioning here. Overall, it is 16. Okay, and this architecture, VGG16, I explained that the layers are organized in blocks. Okay, they made the block like we were having convolution layer, then pooling layer. This is block number 1. Then in another block we are having again convolution, pooling. This is block number 2. Okay. However, the number of filters has been changed in convolution of each and every block. At some place it is 64 number of filter, some place it is 128 number of filter, some place it is 256, and some place it is 512. The number of filters they are increasing. They also told that in VGG16 we have to take the shape of the image is 224, that is the width and the height of the image. That will be the desired shape which VGG16 is expecting for an image. Also, it should be RGB. Okay, it should be RGB, red, green, and blue. It should be a colored image. Okay, yes, ma'am. Any doubt, please let me know.
Sir, I had one doubt. So I understood that the convolution layer basically changes the features like like sharpening brightness that you had explained.
Uh-huh.
I In pooling it does something with a dimension.
Ma'am,
Can you
I will.
explain what?
Ma'am, I will explain everything. I will explain everything. Pooling, I will be teaching separately, madam. Okay, so I will explain everything. That's just a small request, everyone. And madam asked a good question, and I supposed to answer this question, but after some time. Okay, because I need to explain pooling separately. Okay, so let me continue with my flow. Thank you, madam, for asking the question. I will get back to you. Okay, so this is what we are having in VGG 16. I told it is expecting colored images. Okay, fine. Now, let me show you the implementation of VGG 16. I am sharing my entire screen. Please check out here in the code. Okay, I hope you can see the code. Here it is. Okay, we are taking TensorFlow, we are taking layers and models from the TensorFlow. Okay, we have to make a sequential model. That's what we do in neural network. The shape of the image is this thing, 224 comma 3. 3 means RGB, it's a colored image. Number of classes, okay, 1000. Multi classification, so let's see, just putting here 1000. Okay, and now here you can see the layers how VGG 16 is incorporating, how it is adding the layers. Model dot add layer convolution, model dot add layer convolution. Okay, so I add two layers here of convolution, and then I added a pooling layer. Okay, and as we know, in your convolution, I am taking this 3 cross 3 filter matrix. 3 cross 3 filter matrix. Okay, 64 are the number of filters. All right, padding I am going to explain you just ahead, just a second. And then again I am taking the padding same because I need to fill the edges, the borders with 0 in case I'm going to apply this filters and the pooling. So I want this shape of the image to be like in a comfortable mode so that I can be convenient to apply the filter over the image. Okay, so that's why I'm doing the padding. Okay, and we are taking 0 as yesterday, I guess, also, or day before yesterday, also, I told that I'm filling the boundary with 0. So that is the padding. Okay, I will explain more on this. And in pooling, that's a dimensionality reduction technique. Okay, after performing the feature extraction from the image, okay, we are going to reduce the dimension. And here I am taking 2, 2. So it's a matrix of 2 cross 2. Okay, and I am performing max pooling here. Okay, max pooling means a value which is maximum in your matrix will be pooled, will be extracted. Striding 2 2 means you are positioning yourself with a jump of 2 pixels. That also I will show you in my template, in my notes, everything I will show you. So this is my block number 1. How convolution works, that you already know. In my previous lectures I have explained you the mechanism of convolution, how feature extraction has been done. Image matrix with the kernel. Okay, I am having 64 kernels here. Okay, so if a image I am inputting here is 224 it will now become what? After performing this, the depth will become 64. Okay, the depth will now become 64. All right, and the shape of the image will always, obviously, it will be reduced. You know the formula, how the reduction goes on. Again, I will show you in my template. Okay, so two convolution, then pooling, then again two convolution and pooling. This is a standard architecture which is given for VGG 16. The researchers. Okay, however, here the filters are increased. So they did just copy and paste. Number of filter increase. Again, copy and paste. However, here they have increased one more convolution, and the filters are now 256. And then again copy block number 3 and paste. Now here the filters are 512. And again copy block number 4 entire and put it here as a block number 5. Same. This entire block 4 is same. It is repeated. That makes block number 5. Okay. So it's all sequence. All the layers are in a sequence. Convolution, convolution, pooling, then convolution, convolution, pooling, then convolution, 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 then pooling. So that's what they are doing. Okay, and the mechanism is feature extraction, dimensionality reduction, feature extraction, dimensionality reduction. Okay, after performing this all feature extraction and everything, then they performed flatten. Flatten means to convert the result which we got from here in a 1D, one dimensional array. Okay, so higher dimension is converted into one dimension. That is flatten. That will represent the features. Okay, you will get something like this. I have already explained in the previous class. You will get like this. This is flatten. Okay, one, two, three, four, five. Okay, and let me take six, seven. Okay, eight. Might be you are having a matrix here like this. Okay, 4, and this is 6. Let us suppose this is 8. You are having a matrix, 2D matrix, that is converted into 1D with the help of flatten operation. I'm having all the values here. They are called as features. These are the features. And now these features will be given to the neural network where neurons are present. Okay, fine. So what we are having, 4096 neurons. 4096 neurons. Okay, so 4096 neurons are there. Two dense layers are attached after the convolutions, all the convolution operations. And this is one more dense layer which is having four, not four, number of classes I am having is 1000. Okay, so I am having here 1000 neurons. Okay, activation function softmax, because softmax is used for multi classification. It gives the probability. Okay, so as many as number of classes you are having, just fill it here with those numbers. If you are doing multi classification, in case of binary classification, here only one neuron is there, and the activation function will be sigmoid. Remember this thing, that's a difference. In binary classification, one neuron, activation function is sigmoid. In multi-classification, that means more than two. You are having here the number of classes. For example, in our brain tumor, we are having four classes. So I will replace here with four, and I will use the activation function softmax. Okay, so this is the architecture of VGG16. Okay, we can compile this architecture here. Compile means to configure the architecture, because we have because we have added all the layers. Okay, and I need to convert it into operational mode. Okay, so for that you need to configure, because your architecture is only a infrastructure, it's only a setup. Without configuration it will not get converted into active mode, so I need to compile it. Okay, that's what we are doing. So model.compile I did, and here I am having optimizer as Adam. Okay, there is a big story of optimizers, because optimizers are used to reduce the loss in the training, and we mean to get a good accuracy. Loss I'm taking here is a categorical cross entropy. Okay, so cross entropy, I hope you know the concept of entropy. Okay, so we are using here categorical cross entropy. If your classes are binary, then we use binary cross entropy. And if you are having multi classification, then we are using categorical cross entropy. In case you have to one hot encode your classes. Or if you don't do one hot encoding of your classes, then here we use sparse categorical cross entropy, sparse. Okay, right now we are using categorical cross entropy here. Okay, and this is your model summary, the architecture which we have built. Okay, this is the entire model summary. Okay, fine. So we can display the model summary after the configuration of your model. Okay, this is how we make the architecture in computer vision. VGG 16 is just a pre-trained model for you to help you to make you understand that how you can create an architecture. Okay, and because most of the people are here, they are looking forward for, sir, can we make some novel architecture for our projects, for our research? Okay, so from here only we will get a way. From here only we'll get a path. Okay, what we have seen is we have all the convolution and the pooling in sequence. That's what we are having. Okay, so image has been passed here as an input. We are getting the feature extracted or a feature map. That is what we are doing a flatten. And then we are putting this data into the dense layer for training. That's what we are doing. This happens in VGG 16. Okay, now convolution layers, you have already seen how it works. That's we use a formula f dot g. Okay, and we get here a feature map. Okay, this feature map is now given for pooling. In VGG, we have used max pooling. That's a question which been asked to me, that what is this pooling mechanism? What you do in that? Okay, so sir, please explain the initialize the model. Okay, model initialization. Here it is. You just create a model, and after that you have to configure the model. That is compile. Okay, this is initialization means VGG 16 is what I created. I created a method VGG 16. So I am calling this method here. There are different ways you can create the like this codes. So here I am calling this VGG 16 method. Okay, and here I am giving the input shape of the image as this and the number of classes as 1000. And I am defining it as my model. Okay, so VGG 16 is the method I created. Okay, so I got the model and then I'm compiling the model, that is the configuration, and then I'm displaying the summary. Okay, fine. Now, pooling, the question has been asked related to it. What the pooling is? See, after creating feature map, let us suppose this is my feature map. Okay, like this is my feature map 7 9 1 8 2 3 4 5, and then 1 2 7 6 and 2 3 4 7. So I this is your feature map. That means the features which are extracted from the image. Okay, and now it comprises of the information. Okay, and this information I got by the dot product of the image matrix and the filter matrix. That's what I got. Now pooling will extract this information. Okay, and I have used max pooling. There are many pooling techniques. I use max pooling. So max pooling will pick up the maximum information. For example, I am using 2 cross 2 max pooling. Okay, 2 cross 2. So this my matrix is divided into 2 cross 2, 2 cross 2, 2 cross 2, 2 cross 2. You can see in the code. I have performed this 2 cross 2. Okay, max pooling 2 2. So it will make 2 cross 2 in feature map. From there it will pick up the maximum value. Okay, that's what it will do. Fine. So here you can see I will be extracting 8 from here, then I will be extracting 5 from here, I will be extracting 7 from here, and I will be extracting 7 from here. This is what you are going to get from the pooling. Okay, got it. Fine. And then yeah, shape, fine, fine, I will explain ahead. Okay, so I'm going to get this from the max pooling, such values. I need to explain more about this pooling technique because we are having different types of poolings available with us. Okay, and you can see it here in my tutorials related to the pooling. Okay, so pooling is a layer, it is a building block in CNN, and it is applied to the feature map to reduce the spatial size. I'm going to reduce the dimension of the feature map. That is why I'm using the pooling technique. Okay, so ultimately we are downsampling. Reduction means downsample. Reduction in the size is the downsampling. Okay, so this is my feature map. Okay, and I have performed this is convolution feature map. Okay, from the input layer, let us suppose this is your matrix of image. Okay, and you have performed the convolution, and then this is the pooling which has been done. All right. Okay, so max pooling we have performed. Max pooling again, it's a matrix only. Matrix will be created, but the maximum information will be extracted from it. All right, this is how it goes. And we have also seen in the architecture. Okay, we have to perform this pooling operation because dimensionality reduction is one of the technique which we see in machine learning. Okay, we don't want to get trapped in the overfitting. Okay, so we have to select only those dimensions which are necessary for us. All right, so there are different types of pooling: max pooling, average pooling, global max pooling, global average pooling. This is also used majorly. Okay, min pooling also we are having. This is a rare variant, min pooling. In general, we use max pooling. We can use average pooling also. Global average pooling has been also used majorly. Okay, fine. So this is what happened with the pooling. You are having a matrix like this. Okay, and in the max pooling, you can see here 8 is extracted, from here 9 is extracted, from here 7 is extracted, and from here 6 is extracted. You can see the result. This is the output 2 cross 2 which I am getting after the pooling. Okay, and this output which I got, again I'm going to give it to the convolution layer. Then feature extraction will happen. Then again pooling, you are going to perform the dimensionality reduction. So this is what happens in the entire architecture of your CNN. Okay, all convolution pooling are been like attached. These layers are attached, and that's what we have seen in VGG16. Average pooling. Okay, I need to take the average of the values. Okay, for example, this is the feature map. So you have to take the average, like 31 plus 15 plus 100 plus 0 divided by 4, answer is 36. 28, 184, 70, 38, answer is 80. Okay, so this is how you need to perform the average. Okay, got it. Fine. So this is average pooling. Okay, here it is. Fine. We are having global average pooling also. I will show the codes. We'll do the code also for that. In global average pooling, it's a technique commonly used in convolution. I have seen this global average pooling has been more used rather than the flatten. Okay, so it also reduces the spatial dimension. It is applied in the convolution and activation layers in the CNN architectures. Okay, we'll see this thing. Max pooling is also been used. Okay, so global average pooling, it condenses all the feature maps into a single one, all in a single one. All the feature maps are condensed into single one. How it goes, let me show you. See, uh, this is what the global average pooling do. Okay, I will show you the diagram. Here it is. uh, this is my feature map. This is another feature map which is behind it. This is another feature map. This is another feature map. What you have seen in the max pooling and in the average pooling is, you did took these two, then you extracted the max, these, then extracted the max. That's what you have done in max pooling. In average pooling you can take the average of these, but in global average pooling this is not done. In global average pooling it will take the average of all, it will add all. So 3 plus 1 plus 1 plus 3 plus 2 plus 0 plus 5 plus 2 plus 1 plus 4 plus 2 plus 1 plus 4 plus 2 plus 7 plus 4, all divided by how many values are there? 16. So whatever be the result is, divide by 16, you will get the answer as 2.62. That's the answer you will get. If you want, you can check it. This is 4, 5, 8, 10, 15, 17, then 18, then 22, then 24, 25, 29, 31, 38, and 42. Okay, you can do 42 divided by 16. Let me show you over the calculator. Okay, so this is the calculator. Okay, and 42 divided by 16, the answer is 2.625. Okay, got it. This is 2.62. So for a feature map, I got this result. Behind this, another feature map. Again, I will get this result. Then behind this, one more feature map. This result and this result. So it will take the average of all the values rather than was just taking the average of these. This is global average pooling. Okay, got it. So I need to explain this thing as it came as a topic, and in architecture which I am making, I am also including here global average pooling. So global average pooling is a pooling operation designed to replace the flattened layer. Remember, in VGG 16, here you can see in the architecture, we have used flattened layer here, flattened layer. We can replace this flattened layer with global average pooling for better results. Okay, that's what we can do. Okay, this idea is to generate one feature map for each corresponding category of the classification in the last layer. One feature map. Not usually the feature maps of the last convolution are vectorized and fed into fully connected. Okay, vectorization has been done and they are put into the dense layer for the training purpose. Okay, global average pooling replaces this strategy. It takes the average. That's what we did. It takes the average of the feature map and feeds the resultant vector into softmax layer rather than constructing fully connected layers to top on the top of the feature map. It directly feeds this thing into the softmax layer for classification. That's what it will do. Okay, and we are going to incorporate this global average pooling in our architecture also. Fine, got it. That's what we have to do. Okay, so the purpose of global average pooling is again to reduce the spatial dimension. For each channel in the input, it takes the average of all the pixel. We have taken the average of all the pixels across the height and the width. Okay, we have taken the entire stuff and we have taken the average of all, reduces the dimension. Often used at the end of the convolution. Okay, obviously, it's going to replace the flatten. So instead of flatten, use global average pooling. So it will reduce the number of parameters and help to prevent the overfitting. That's why we are using global average pooling, reduction of overfitting. Okay, it's commonly used in mobile net and Inception, such kind of architecture. And yes, they have given the good results for me. Inception, Exception, mobile net, they have given good results with attention mechanism to me. Okay, so this is pooling, dimensionality reduction. Different kinds of pooling, but you have to focus upon either max pooling or either global average pooling. These two are the ones which are mostly used. Global average pooling is used as at the last. Don't include global average pooling in the intermediate. No, don't do this thing. If you are looking forward to, sir, can we use global average pooling here? Model dot add global average. Nah, don't do that. Global average pooling is a substitute of flatten. Okay, fine. Okay, so here these are the hyperparameters which we have seen in the architecture: filter size. Okay, 3 cross 3, 5 cross 5, 4 cross 4, 2 cross 2 is not used. Always we use odd. The reason why we use odd filters I have explained in the previous lectures. Because it will cover your edges, boundaries, also the central pixel. Okay, striding, I already told you. The number of steps the filter takes to traverse the image. This is 2 steps, 2 steps. That means 2 pixels it will cover. This is striding. Okay, this is two cross 2 filter stride on 4 cross 4 matrix. So the result is 2 cross 2. Okay, fine. So result is 2 cross 2. Okay, got it. And this is one striding, one. This is one. That means your kernel is moving on image one pixel by one pixel by one pixel, one, and this is like this. It is moving, and in two it is moving two steps, two pixels. That is called as striding, and from left to right and down also. Okay, from top to bottom. That's what it is moving. Okay, fine. Padding, yes. There is also padding in VGG16. Padding, like sometimes filter size creates border effect. Okay, it creates border effect. This effect can be overcome through padding. I already told you that performing convolution, traversing kernel over the image can create some issue at the borders. So the border effect refers to the fact that as a filter traverses a feature map, the border elements are generally much less used. When there is a traversing, the border elements, the information which is present at the border is less used. Also, the size of the image sets a limitation to how many times can an image be pulled. As pooling decreases the size, you can see I already raised this issue in the previous class also. If you perform the pooling, if you perform the convolution also, the size of the image is continuously decreasing. You started with 224, you ended up with 7, 7. So this, how much size has been reduced? This is your result. This is your result which you got. Okay, and the final tensor you are getting is 772048. And if you are having one image, so you have to put one, and if you are having 1000 image, then you have to put 1000 here. Yesterday only I have explained. This is your number of samples, or your number of images. This is width, this is height, and this is the depth of the channel. After convolution, this is what you are going to get. After the entire convolution, all the blocks, this is what you are going to get. Depth will increase, however the size of the image will decrease. So there are certain issues. So I need to perform the padding, I need to manage the size of the image. So here I am taking padding equal to same. So let's say we are filling with the zeros. You can see at the borders, zeros are filling. This is zero padding. Okay, zero also represent like an information. Okay, so here every bit is like an information, every number is an information. So on the edges we have filled with the zero. So that's what we call as a padding. So padding is done in a situation. That's what we have already talked about at a border to our feature matrix. So once you get the feature matrix, add the zeros. So here we did seen in the VGG16, you can say padding same everywhere, padding same. After every convolution, this person, this scientist researchers, they have used padding same everywhere. So you should get an idea what an issue can be raised in an while performing the feature extraction in image. And if you have to make your own architecture, you have to focus upon these points. Activation relu, okay, you very well know about this activation function. Also there are many activation functions. Okay, and activation function ReLU stands for rectified linear unit. And I already told in the previous lecture, when input is negative, then output is 0 by ReLU. And if the input is positive, then the output is same, whatever be the number is. This is what ReLU do. So I will be having positive numbers. I will be having positive numbers. So once your feature map passes through ReLU activation function, if there is any negative number, that will be turned up to 0. And this is what you are going to get, like this. So ReLU is a famous activation function which is used in artificial neural network and in convolution neural network. In these two, ReLU is used. In in text, in text, that is when we are performing sequence. In text there is a sequence, we do perform sequence classification. There sigmoid or 10h activation function are used. Okay, there these two are used. In CNN relu is used. Okay, so just remember this thing, relu. Okay, fine. All right. So padding also, why we are doing the padding, everything is mentioned, it's all I did talked about. And you know that once, like, your kernel performs the operation with the image matrix, this is what you are going to get as a feature map. So this is your feature map. Okay, fine. Formula also I have explained you in the previous class. Okay, what is the resultant feature map we are going to get? Okay, so this is the formula. This is height of the image. This is the height of the kernel. 2p, p means the padding, how much padding you are doing. S is the striding. It will give you the height of the resultant matrix or the feature map. This formula is same here also. Only the thing is here I am taking the width. So this is the width of the image. This is the width of the kernel. This is again padding. This is striding. Okay, that's it. This is the number of channel. So by applying this formula, I will get the resultant, the feature map dimension. Okay, got it. And now let me show you the codes. Okay, let's see the codes for them. Okay, so here it is. How to apply pooling, sir? If we are having a matrix, so can you tell me that how the pooling is applied, sir? Okay, NumPy, numerical Python. Again, I am taking sequential model. Okay, and I am taking max pooling layer from the Keras. That's what I am taking. Okay, max pooling layer from the Keras. Okay, this is my image matrix. Okay, and you can show this image matrix also in a grayscale. Then I perform the reshape of this image. 1441. That means 4 cross 4 grayscale, and I am having only one image. Now you should be confident enough to understand what it is. So reshape this 4 cross 4 into 1441. Convert it into a tensor. Okay, so now it's a tensor. And then you give this image to the pooling layer. So I am just creating a architecture which is just having a pooling layer. No convolution, just a pooling. Yes, you can do that. It's not mandatory that you have to take convolution and only and then no. And it's not also mandatory to take pooling. You can take convolution, convolution, convolution also. Every kind of experiment you can do with this. So at the moment, I'm just taking a pooling layer. Okay, and I am giving the image to this model which is having a pooling layer. Okay, to perform the prediction. Okay, and here is the output which I will perform the squeeze. Okay, squeeze, that means I'm going to get the answer like, okay, you can see after a pooling operation it will reduce the spatial feature of your image. Okay, fine. And yeah, I think that's okay. So this is your initial image. This is your initial image, and after pooling you can see what happened. After pulling, after max pulling, what you got? The answer is 11, 10, 16, and 2. These values you got. So 11, 10, 16, and 2. This is what you got after pooling. Okay, because you created a pool of size 2, that means 2 cross 2. Striding you perform 2. That means 2 pixel you are jumping. Okay, so if you put this thing into the formula, into that particular formula, okay, so you will get the size, and the size I'm getting here is 2 cross 2. This is the size which I'm getting. This is your result for the max pooling. Okay, so converting the result into a NumPy array, okay, and printing the output. So this is what you got. Okay, yeah, here it is. This is your squeeze results. You are having higher dimension that has been reduced to this dimension, 2 cross 2, 2D. And this is your max pooling result. Okay, a simple code where I am available with the image matrix and I perform the pooling of it. And this is how it looks like. Then I have performed average pooling also. If you want to see, sir, how average pooling works, again take an image array. Okay, and make a model which is having only average pooling. Okay, give this image to the model and just skews it. Okay, so this is the result which I'm getting after average pooling. And this is the metrics for average pooling. Striding again, you did of 2. Okay, pool stride, striding 2, pool size is 2. That means 2 cross 2, and striding is by 2. Okay, so it will be like 1, 5, 3, 11. It will start from here. Then it will jump to here, 10, 6, 9, 6. So 1, 5, 1 plus 5 plus 11 plus 3. How much it is? So 1 plus 5, 6, 6 plus 11 is 17. 17 plus 3 is 20. Okay, and 20, and this will be 4 elements now. Okay, so 20 by 4, answer is 5. And here also the same thing. 10 plus 6 plus 6 plus 9. So it will be 10, 16, 22, and 9. So it is 31. 31 by 4, it is 7.75. This is average pooling. Okay, min pooling, fine. I guess you very well know about the min pooling. What average pooling you do know, you know about the min, like max pooling. So min pooling is just extracting the minimum value. Okay, fine. That's what we have to do. And here it is global average pooling. Okay, so I am just adding a global average pooling layer in the sequential model to perform the prediction. Okay, and give your image into the model. And this is what you are going to get the result, 5.5625. You are having only one image, so only one answer you are getting. With one image, one answer. If you are having one feature map, one answer. Why? You can see. You can do this thing. 1 plus 5 plus 10 plus 6 plus 6 plus 9 plus 11 plus 3 plus 4, and you just add all the values divided by 16. Definitely you will get this answer only, 5.5625. This is global average pooling. Okay, got it. And we are going to use it at the last of your convolution pooling and all these things. And at the last, you'll use global average pooling instead of flatten. So you will get a value. You will get a value for a feature map. Because now again I will show you. Let's show this thing diagrammatically again. I think I am available with this diagram also related to the flatten. Here it is. This is what flatten do. If you are having a 2D matrix like 3 1 1 2 5 0 1 4 2, if you apply flatten now, so it will arrange the values like this. It will arrange the value 311, okay, like 311, and below that 250, and below that 142. So it will convert it into 1D. Flatten converts high dimensional data to one dimensional data. But instead of doing this thing, instead of arranging them, for example, this is my one of the feature map. Flatten is arranging all these values. So this is my 3 cross 3. Flatten will convert it into 9 cross 1. But what is global average pooling is doing? It's saying, no, 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 I'm not going to do that. Global average pooling will do the sum of all and divided it by 9, because there are 9 values here. And it will give you only one value rather than giving all these 9 values. No. That is the difference between flatten and the global average pooling. I hope this makes sense. This is the difference between flatten and the global average pooling. So I hope you have seen computer vision students. You have seen this layers, and now I have clarified what is the difference between these two. Okay, fine. Now, so global average pooling does something different, and that's what it do. I have already explained what it do. Okay, here it's mentioned. Okay, fine. So here in my architectures which I'm going to use, I will be using the global average pooling. So what I explained you so far, you now know about convolution. Now you know about pooling also. You know about kernel. You know about striding. All these things you very well know. Okay, fine. We are having dense layers also. Okay, so the dense layers comes after all this convolution. Then we are having a neural network. So at the neural network, we are having dense layer. Dense layers are fully connected. They are available with the like neurons, neural network. So that's what dense layer do. Okay, got it. And then at neurons, we do perform activation also like ReLU, sigmoid. That's what we do. One more thing I want to discuss about. I hope you have seen this dropout and batch normalization also. These two layers also you have seen. These two are for overfitting, to prevent overfitting. Prevent overfitting in the model. These two layers, dropout and batch normalization. Okay, dropout means, okay, either you can say regularization technique, rather you can say to prevent overfitting. Both means the same. Regularization, it's like a penalty. It's like a penalty which we give to the model if the model is overfitting. Okay, so if you add so many neurons in the architecture, as we have seen in the architecture also 4000, here you can see you got 4096 neurons here in the dense layer. Sometimes it happens that considering each and every neuron in the layer na, it can create an issue of that overfitting. So dropout layer and batch normalization, these are the two layers which we can introduce in between. They skip, for example, dropout. If I say zero point 0.5 instead of 4096, if I drop out 50% of the neurons, so only 2048 neurons will be active. Rest 50% of the neurons will be deactivated. That's what happens in the dropout. So in a iteration, in a particular epo, if you have given dropout zero point 0.5, so 50% of the neurons will not get trained, only 50% will get trained. And in the next iteration, those 50% were trained previously were now behave as deactivated, and the previous deactivated will work as a activated. They will get trained. Okay, I do have the discussion related to it in detail also. A fraction of neuron are randomly set to 0 at each training step. How much fraction you can mention? Zero point 0.5, zero point 0.2. In case if your model is overfitting, you have to you have to introduce dropout. The example they gave, dropout 50%, zero point 0.5 means 50% of the neurons in the layer during each training iteration is switched off. It's switched off. I don't want my brain to learn everything. Actually, it's not learning now, it's memorizing. Learning is something different. It's memorizing. I don't want a memorization. Okay, so switch off, turn off some fraction of the neurons. Batch normalization. Again, it's a regularization technique. It's normalization. Normalization means the inputs to the layer, we want mean of 0 and variance of 1 to improve the training speed and the stability. We want the data which is given should be normalized, where its distribution should be like mean should be 0 and variance should have to be 1. Okay, why it's saying like this, let me explain you. For example, you are having a data like this. You are having a data where certain features are available, like x1, x2, x3, x4. These are the features which are available in your data. One feature is having a values 1000, 2000, 1000, then 3000. One feature is having a value 10, 5, 12, 10, something like that. Another feature is having a value 1, 2, 3, 4. Another feature is having a value 50, 100, 150, 200. So you can see that these features are having the values. Some are very large, some are very small, some are like medium, and this is very medium. So the distribution of the values are different here. Because the distribution of values are different here, there is one concept which I say. This feature is having huge amount of value, means the variance is high. If the values are high, variance is high. Because the variance is high, this feature will say, boss, I am having high variance. My values are larger, and you are having low values. So you are poor, and I am rich. So that is the general tendency that rich are going to dominate the poor. That's the general tendency. So my model will be much more influenced by the rich people rather than the poor people. So what does batch normalization do? It try to normalize, it try to make a balance between the features which are having a difference. There should not be any like dissimilarity. So let's scale the data. Let's normalize the data. That's what they are saying. The distribution of the data, they are saying that the mean should have to be like 0 and the standard deviation should have to be like 1. That's what they are proposing. The distribution of the data here, if you just check the distribution of all these, they should follow this kind of values according to the statistics. So we do have to normalize our data in order to reject this effect. Okay, got it. So it calculates the mean and the variance of the inputs for each batch, applies normalization transformation. That means to convert that data into particular range, we need to apply normalization transformation. Okay, commonly placed between the layers of deep networks, usually after the activation. After activation, normalize. Okay, again, it helps in smoothing the process of training. Okay, and we never expect that, okay, one value is 100, one value is 10. No, we expect normalized values. If the distribution of the data is disturbed, your answer will be disturbed. Remember, अच्छी खासी कहानी है इसकी. सब डिस्टर्ब हो जाएगा, नॉर्मलाइज नहीं करा तो आपने. यू हैव टू नॉर्मलाइज ताकि डिस्ट्रीब्यूशन ऑफ डेटा को मेंटेन रखो आप. If you don't do the normalization, the values will be some are high, some are low, some are medium. Obviously, you are not going to get the good answer. So, batch normalization. ओके, तो ड्रॉप आउट भी करने का. ये डेंस लेयर है, ड्रॉप आउट है, नॉर्मलाइजेशन ऑल्सो वी नीड टू डू. वन मोर लेयर, वन मोर थिंग विच आई एम गोइंग टू ऐड इज द नॉइस. मैं क्या कर रहा हूं, नॉइस भी ऐड कर रहा हूं अब. नॉइस इज द रैंडम डेटा पॉइंट्स. Noise are the random data points. Now the question is, sir, you are already having the data. You are already having data. You are getting the information, sir. Why you are adding the noise in the data, sir? Again, see, भाई मॉडल को स्ट्रगल करने दो यार, उसको सीखने दो. We want the model to learn the variation. We don't want to give a model, ले बेटा ये प्लेट में तेरे को खाना लेकर आ गया, खा ले ये. We don't want to deliver a model, a prepared food in front of it and ask, let's get a treat from us. No, I want to add variation in the data, because in real world you may have different variations in the data. So adding a noise, adding a Gaussian noise. Okay, during training, a random Gaussian noise, zero centered, with a standard deviation specified by the user, you can give. So in order to prevent the overfitting. Okay, overfitting. When it will be overfitting? If you feed the model a pattern of the data which is same. If you are feeding the model same pattern data, so it will get overfitted. Na? Because once it goes on testing, you may get a different variation on the image. So your model, in training model will say, yes, yes, boss, I am good. But during testing, the model will fail, because the model is not learned to accept the variation in the data. That's the reason I'm going to add the variation in form of noise. That's what I will be doing. Got it? Region. Okay, fine. Yes, Sarthak, you got some question?
Yes, sir. So the increasing noise in the data set increases the accuracy of the model, right?
Increasing the noise, it will prevent the overfitting specially. Okay, so that's what I want to do now. I want to make a model to learn the different patterns in the data. What is machine learning? What is deep learning? What is this we are doing? We are making a machine to learn the patterns only in the data. And we are applying all these maths for this reason only, to learn the patterns. Okay, Sarthak.
Yes, sir. Yes.
Kaur madam, do you have any questions related to the pooling as you were asking previously?
Yes, sir. Now I understood. Thank you.
Okay, if you have any issues, then you can pick up now, because I have 1 hour I spent. If you have any doubts, you can call up. Yes, Sumit sir. Any doubt, please let me know. Then I will proceed ahead.
Sir, are you getting my voice?
Yes, yes, sir. Please say.
Sir, you explained the normalization in terms of text. So, what is normalization in terms of images?
Huh. So normalization in terms of images, that's what I explained, sir. Okay, I'm available with the formula also related to it. Let me show you the formula. I've also explained the normalization in terms of text also. Okay, so in my basic classes related, this is the formula for the normalization. Okay, so batch normalization is applied to layers that you choose to apply. I hope you have seen a formula of standard scalar. X minus nu upon sigma. This is standard scalar. There are very different scaling techniques. This is one of the technique that is called a standard scalar, and you can follow by this thing. Z equal to Z is called as Z score. It's a standard scalar only. It's a scaling technique. From here, whatever be the output which we are getting, okay, batch mean is subtracted, and the whole thing is divided by the standard deviation. That's what they are saying. Standard scalar. After that, the batch normalization is multiplied the normalized output with some arbitrary parameter. Let us suppose f. There is one parameter, we have to multiply a result with this particular parameter. Finally, batch normalization adds with arbitrary parameter to this above product, like this z equal to z into f plus b. You can relate it with this equation y equal to mx plus c. That's how you can relate. Okay, and what these parameters are, let me clear you. These parameters are nothing but nu and sigma only. These parameters are that only. Okay, you're taking the f and b. These are nu and sigma only. Okay, so what the normalization? What's the formula? Maths for the normalization. X minus nu upon sigma. You are going to get a result. Scaled data. X is your input value. Nu is the mean. Sigma is the standard deviation. Okay, you will get a value. Let us suppose you are getting a value S. This S dot nu plus sigma. This is our batch normalization. Final result. And here it's been said. All these parameters, M, S, F, V, are trainable. Trainable means during training they will be adjusted. That's what we call as a train. This is the formula, sir. And please don't forget this standard scalar, scaling technique. And when I gave you the explanation here, wo poor and rich wala, the explanation which I gave here, poor and the rich, you have to take the mean. Take the mean, nu 1, nu 2, nu 3, nu 4. Calculate the standard deviation of each column also. And then from every value, 1000 minus nu 1 divided by sigma 1. Then the values which you are going to get here are the scaled values. That is what standard scalar is. That is what we call as a normalization. And for training, they already told you. Okay, what? This thing. What is been scaled? So with nu plus sigma. This is the equation. Okay, this is the equation in batch normalization. Okay, fine. So yes. So this is not. I have put some part of maths also here in the notes. You are available with the notes. Okay, so let me get back to my code. That is your brain tumor classification. Okay. Yeah, here. So, like in the yesterday's class, we have already performed the oversampling and we have made all the classes equal. 6380, all the classes equal. And why I did perform oversampling, I already explained. Okay, making things equal. After that, this is your data frame. Okay, now I imported the libraries. What next I need to do? So I imported the TensorFlow, Keras, sequential model, optimizer, and these convolution layers. Max pooling I explained. flatten I explained, dense I explained, activation function, I explained ReLU, dropout I explained, batch normalization also I explained. I will follow up more on this. If you have any difficulty, I follow up more on this. No worries. So this is my major part of the libraries which I'm going to include. These are deep learning libraries. Okay, fine. Explanation I have already given in the code, you can follow, but that's not so much needed. I have encoded now you 1, 2, 3, 4, like the numerical values as a target categories. I convert them into string. Let's convert them into string. They will remain as a number, but now the data type will be behave as a string. Data type will be as a string now. Okay, so what you are available with? You are available with a balanced data with all the categories are there. Categories 0, 1, 2, 3, 4 classes are there. All the categories are there. Image path is there. Okay, and these category are string type. I need to convert, that's why I did. Okay, then what I did? Let's split your data. Split your data into training, testing, and the validation. This code says the step. Train test split. This is your data. 80% I am taking for the training purpose. I am shuffling this training data also. Why shuffling? Because I don't want to get the model. Okay, I am feeding you. Okay, I am feeding. Just take the data in a regular pattern. No, shuffle करो shuffle data को. कभी भी मॉडल को एक जैसा नहीं पकड़ाने का डेटा शफल करके दो और जो भी चेंजेस कर सको नॉइस ऐड करना है दैट आई विल टेल यू ये करके दो आप ताकि मॉडल को वी वांट इट टू लर्न ओके शफल कर दिया मैंने ट्रेनिंग डेटा 80% आई पिक्ड एंड आई शफल्ड इट रैंडम स्टेट 42 तो ट्रेनिंग में चेंज मतलब वो वाली बात नहीं है फिर स्ट्रेटिफाई इसलिए करा है क्योंकि इक्वल पोर्शन जाना चाहिए ओके दैट इज वाई आई टुक स्ट्रेटिफाइड क्लासिफिकेशन कर रहे हो ना तो 0 क्लास 1 क्लास 2 क्लास एंड द 3 क्लास 4 क्लासेस आई एम हैविंग सो like the proportion should have to be same for all these. That is why stratify. I made training data frame and temporary data frame. 80% of the data will go in training, 20% will come in temporary. Then again I took temporary and I splitted it 50%. That means 20%, I am having 20% in the temporary. That is divided into 10%. 10% validation, 10% testing. Shuffle true. Same. So 80% training, 10% testing, 10% validation. This is what I did. Got it. And then what see? Let's talk about some pre-processing technique also. I'm taking batch size 16. 16 here, I'm picking up the images in a batch of 16, 16. 224, 224. See, boss, you have to do this. 2224, 224, 224. Because if you are using a pre-trained model, VGG16, the expectation of VGG16 is 224, 224. Color RGB 3. So you have to convert your image into 224, 2243. Initially, your images are grayscale images. Check. Your brain tumor images are grayscale images. ये कोई colored थोड़ी ना है. These are grayscale images. So I need to make the shape of each and every image is 224, 224. उसको colored बनाना है. तो 3 करना है. और ये भी मैंने I already explained this thing in my initial lectures that if you convert the grayscale information into RGB, 2 more components, 2 more channels are added, and the same information is shared on the additional channels. तो कुछ होगा नहीं, वो रहेंगे ग्रे स्केल. Okay, बस complexity increase. No, we are not bothering about the complexity. All right, fine. So yes, हो गया. Then I'm rescaling. I'm normalizing the images. See, Normalize, divided by 255. Every image, what you did, you converted a image into 224. So this is 224 cross 224, 224 in a row, 224 in a column, and the entries will be like 110, 120, 220, something like that. The entries will be there. 1 by 255 means you have to divide 255 with each and every value. So it will be now become 0 to 1. Every value in an image will now convert between 0 to 1. This is called as normalization. You're scaling your data, scaled to 0 to 1. Mandatory, भाई ये हो जाएगा, एक वैल्यू हो जाएगी 1, एक वैल्यू यदि 220 हो गई ना तो मजे आ जाएंगे. यही तो सिखाया था. That's what I taught you just recently. Why to normalize? Because if a pixel value is 1 and if a pixel value is 220, this pixel is rich, this pixel is poor. So the poor pixel will be suppressed by the rich pixel. Okay, got it. I want everyone to stay with me. We are dealing with a very interesting like phase of our this session. Okay, so perform scaling, rescale, divide every, in training data also, in testing data also, divide each and every pixel by 255 to convert it into between 0 to 1. अब सब 0 से 1 के बीच में आ गए. लो बेटा अब क्या होगा? ठीक है. Then this is train generator. That means whatever be the operation I need to follow, these are the things which I need to follow. Let me take my training data, let me take the image path, let me take the label. Training size should be 224, 224. Class mode is sparse. Sparse means multi classification. I am having 4 classes now, so I will be using sparse. RGB is a color mode. वो 3 कलर है ना, 3 चैनल, तो RGB. Shuffle तो करना ही है. So training data, you perform this operation. Okay, create a batch size of 16, convert the images into this channel, this. Perform this over training data. Perform the same thing over validation data. Perform the same thing over testing data. But remember one issue. टेस्टिंग को भैया, टेस्टिंग को शफल मत कर देना. वी डोंट शफल द टेस्टिंग. टेस्टिंग को शफल नहीं करते. ट्रेनिंग एंड वैलिडेशन शफल करके देंगे. टेस्टिंग विल नॉट गिव बाय शफलिंग, because once your model got trained, then we will do the prediction from the model over the test data. अब यदि तुम टेस्ट को शफल कर दोगे ना, तो जो प्रिडिक्शन विच यू आर गेटिंग एंड द शफल्ड, वो शफलिंग होने के बाद पूरा ऊपर नीचे ऑर्डर हो जाएगा, तो कंपेयर नहीं होगा. देयर विल बी नो कंपैरिजन. तो टेस्ट को कभी शफल नहीं करते. ट्रेनिंग एंड वैलिडेशन यू कैन शफल. Alright, got it. That's it. So I'm having this much number of images, 20,000 in training, 2,552 in validation, 2,552 in testing. Okay, मिल गया, बस खत्म बात. उठा लो TensorFlow. Okay, TensorFlow layers models. I'm taking early stopping and the model checkpoint. Early stopping I'm using in case if you have entertained 100 epos in your training, and after 10 epos your model is not at all learning, so it will stop. Early stopping is a condition. If your model is not learning, so by giving early stopping it will stop. There's a condition. Else you have to wait for 1000 iterations, unless and until your, or 100 iterations, unless and until your entire training program is not completed. So it's better to give early stopping. And we are also checking model checkpoint. So what are the trained weights we are getting, so that can be done with the model checkpoint. Okay, it saved the model during the training. Okay, and early stopping, we are going to monitor the model progress. If it is not progressing, stop. Don't wait for completing all the iterations. That is early stopping. Okay, I am using the GPU, because once you are using this training, image training, yeah, text training, you're using heavy models, pre-trained model, then you have to apply the GPU. And you can take the GPU once you edit my code now. So there is available accelerator in Kaggle. Accelerator, you select T4. Okay, GPU T4, you can select. So I'm using the GPU, graphics processing unit. Okay, fine. I'm going to monitor the loss for the validation, and I'm going to keep the patience for five iterations. I will keep patience. If there is no change in the training, stop. That's it. Okay, got it. This is my VGG16. So from TensorFlow, Keras application, import VGG16, import the layers, take Atom as an optimizer, create VGG16 method in which you are going to give the image of 224 224. Okay, just take the input shape 224 224. See, VGG16 is already pre-trained model over ImageNet data. It is already pre-trained over ImageNet data. Okay, fine. So we have to download the weights of VGG16, trained weights of VGG16. VGG16, the 16 layers which you have seen here. Boss, we are not going to train this entire model. No, we are not going to train this entire model. No, we will be just taking the weights of this model which is trained over ImageNet data. ImageNet, I already told, which is having, it's a benchmark data which is having millions of images. So we will just pick up, we'll just take the trained weights, parameters, parameter values from this model. And initial model, we will say, for layer in base model dot layers, layer dot trainable false, whatever be the layers which are present in my base model, that is VGG16, I will say don't train yourself, false. Okay, this is what we have to do. It's transfer learning. So false. Don't train VGG16. Just take the weights from the VGG16. Then this is whatever be the output you are going to get from the base model, give it to X. Okay, and then height, width, and the channel 77512. See what you get from VGG16. What you get from VGG16 here. You can see at the last. This is the max pooling 77512. So after application of VGG16 layers, the result which you get before this is flattened, not this thing, this 7712 512. This is what you are going to get. Okay, yeah, please say. If you can comment on the code with yes, I will be commenting on the code. Okay, I will comment on the code. So, what is the reason for 77512? Because in the last convolution, pooling layer of the VGG16, this is the shape which we are getting of the image. So, we have to start with this shape by performing the reshape. Just start from the 77512. Input, it will take the input 224 224. But that will be converted to 77512 according to the architecture of VGG16. The last one is 77512. Okay, fine. हाँ, अब भाई मैंने लगाया है attention mechanism. This is for what the people are here. Sir, what is the novelty you have introduced in the architecture? What is this attention mechanism? Attention mechanism become very much famous in large language models, LLMs. You know chat gpt. So chat gpt is based upon this attention mechanism only. Attention mechanism. What is this attention mechanism do? Attention mechanism keeps focus on, or it will focus or it will attend the features. That's what it will do. Attention. Okay. So sir, how it works sir, how it's going to attend, what focus are you talking about? किस focus की बात कर रहे हो आप? किस पे focus करना है? कैसे करना है focus? How? तो हुआ ये, this concept become more popular in your text in LLMs. However, the concept, and it's part of transformer architecture. Transformer architecture. Okay, fine. Transformer. In transformer, you are having encoder and decoder, two components. In encoder also I am having attention. In decoder also I am having attention. What is present in the attention? Okay, let me tell you. In attention, you are having three components: Q, K, V. Query, key, value. Three components you do have in an attention mechanism. Okay. So, sir, what does QKV means, sir? All right, let me tell you. These are vectors. These are vectors. Okay. Now, sir, can you please tell more about it? Yes, let me tell you more about it. In text, let me take a simple example of text. If you are having a sentence like my name is Nirmal. Okay. In text, it do tokens. That means it consider each and every word. That is called as tokenization. टुकड़े करता है वो, tokens. Okay. Then what it will do is it will create a matrix. My name is Nirmal. My name is Nirmal. It will create a matrix. Okay, fine. Like this. And then it takes a dot product. Every word is been represented by a vector. Then it take the dot product. My to my dot product. My to name dot product. My to is dot product. My to Nirmal dot product. Similarly, name to my dot product, and like this. It will take the dot product. Okay. So it's actually Q dot K. Okay, I can take this as a vector. I can take this as a vector, v1, v2. I can take the vectors. That's what I have mentioned here. So just take the dot product. After taking the dot product, we have to scale the values. Scale. Okay, scaling is done by like square root of d. D is any parameter. So perform the scaling. So q dot k square root of d. For dot product, let's take the transpose. Okay, because this is how you do the dot product of vector. This value and this value dot products, one by one. Okay, one by one. Got it. So q dot k divided by square root of t. And then you have to apply a sortmax function, sortmax activation function. Whatever be the results you are getting, apply sortmax activation function. This is called as attention mechanism. This is what happens in transformer in large language models. Attention mechanism. I am incorporating attention in my pre-trained models. For that, I have also created a numerical for you to get a better explanation. Here is the numerical. Here is the numerical. Let us and I started with, okay, convolution, then what happens, then what happens. I introduce attention. Consider an image of size 4 cross 4, one channel. That is a grayscale image. Filter 3 cross 3 we are taking. On only one filter we are taking. So we are having an image, we are having a filter. Okay, let us suppose this is your image. These are the values of your image, 4 cross 4. Let us suppose this is your 3 cross 3 filter. Okay, and you have mentioned that striding is 1, padding is, there is no padding. There is no padding. Striding is 1. 1 pixel by 1 pixel you will move. Okay, so if you apply 4 cross 4, 3 cross 3, if you apply this, this is the dot product, if you apply, that's what happens in the convolution, you will get a feature map. And the feature map dimension will be, this will be the height of that, and this will be the width of that. Every calculation is present here. And this is what you are getting after convolution. Okay, so this is the first position, this is the second position, and this is third, and so on. The positions are calculated. So the result which you are getting here is minus 6, minus 6, minus 6, minus 6. That's what you are getting. Okay, minus 6, minus 6, minus 6, minus 6. That means 4 cross 4 matrix, then dot product by your kernel, and then you got a feature map. This thing. This is what we have done. We do every time. Then you have to reshape it. The output of the feature map, that is 2 cross 2 with one channel, that is the shape 2 2 1. Now we need to reshape it into a vector to use attention layer. After convolution, I have added attention layer. To do this, we flatten the output in a shape of 4 1. So let's reshape and convert it into 4 1. 4 row, 1 column. This is what I did. Minus 6, minus 6, minus 6, minus, all come in a all single row. That means 4 rows all comes like this. There is one column, single column. And then you can incorporate attention mechanism. The attention mechanism computes weighted sum of the values, where query and the value are same in self attention. Query and the value are same. See here in my example also, you can see my name is Nirmal. My name is Nirmal. I took the dot product now, q dot k. So let us suppose this is query, this is key. I took the dot product of these two. The query and key are same. That's how I took initially. Just for simplification, I'm explaining. Okay, so they are saying that I need to compute weighted sum of values where query and value are the same. In simple scenario, let's assume that query and the value vectors are just reshaped feature maps. That means they are just all minus 6, minus 6, minus 6, and minus 6. That's what they are. This is query and this is the value only. Query and the value. Okay, there was a key. Okay, I just shown you a key. ये तो key थी, ये की थी. ओके, तो उसको मत लेना कभी, ठीक है. ये क्वेरी और की का डॉट प्रोडक्ट था. Currently I am talking about query and the value. Okay, so just focus here. For simplicity, we assume a dot product attention where this is the formula, and I have already shown you the formula. Okay, q dot k ka transpose divided by square root of d. I need to take the shortmax activation function, then I need to multiply by v also. That's what I think I should have to mention here. Here, I need to multiply it with v. This is attention mechanism. Okay, just again wait. So given query and the value are same, The dimension is 1. Let's decay one dimensional. You are having one dimensional data, that is minus 6 minus 6 minus 6 minus, this is 1D. Okay, so 4 cross 1, that is like 1D vector. Okay, for simplicity we are taking, and then we can apply the attention mechanism which I have mentioned here, q k transpose square root of d by v. How this is multiplied, how this is done, let me show you here. Okay, this is your feature map which you got, 4 cross 1. Step 1 is to apply a transformation for creating query key and the value. That's what you have to make, query key and the value. Okay, so let us suppose query key value are all same, minus 6, all these things, minus 6 minus 6 minus 6. Let us suppose they all are same. So the first thing is you need to take the dot product. Okay, that is q dot k, q dot k ka transpose. That's what you have to do. Okay, so this is q, this is k, take the dot product, q dot k ka transpose. So the result you are getting is 144. And then you have to you have to scale the attention score. You have to do the scaling. So q dot k ka transpose divided by square root of d. So d here dimension, they are saying that 4 cross 1, so d is 4. So 144 divided by square root of 4, that is 2, so it's 72 is the answer. Then you have to take shortmax normalization. So we will apply the shortness function to the attention scores in self attention. We often calculate the score for each query with respect to all the keys, but in this simplified case, we have only one query, one key, so the shortmax will yield the value 1. The answer will be 1 because we are having one query only. The answer will be 1. Okay, and okay, answer will be 1 for that. That means that result will be existing. For a single score S, the shortmax is 1. Now I need to take the weighted sum. Finally, we compute the weighted sum of the values based upon the shortmax scores. We only have one query, one key, and the value. The shortness score is 1. The output of attention mechanism will be simple a value vector. That means this is your shortmax. If you apply on the attention score, answer is 1. Multiply by the value. Value is minus 6 minus 6 minus 6 minus 6. So 1 into this is same. Minus 6 minus 6 minus 6 and minus 6. This is your answer. The final output is this only. Okay, that's your final output. Okay, so what's the lesson we have learned here? What's the lesson? The lesson is Q, K, V. These three metrics, these three vectors, you have to make. How you are going to make? How you are going to make? You performed, this is your image matrix. You give input this image to the convolution. Convolution is having filter. So this image with filter dot product, you got feature map. Feature map, okay, this is a matrix. Now this matrix, you have to pass through attention layer. In attention layer, you are having three components, Q, K, and V. You are not passing this to convolution to pooling right now. Okay, not pooling right now. I've introduced convolution after attention. Okay, that means convolution then attention. That's how introduced. Okay, so you have to apply the feature map pass through QKV. Okay, for that you have to convert this. You have to reshape this. That's what you did. Like 4. Okay, what's the result which you got after feature map? You got such kind of result. Okay, and you perform the reshape to convert it into 4 cross 1. You converted it into 4 cross 1 by doing the reshape. And then you said that this 4 cross 1, let us suppose the answer which I got from the feature map, that is q, that is k, that is we all are having the same value. Let's suppose this thing only. They all are having the same value. Just next, I need to put these all into this formula. Q dot k ka transpose ka square root of d. Then I need to take the sortmax activation function dot v. That is what I need to do. Okay, now let me more simplify. Query. You know about SQL. You fire a query. That query goes to the database. From database, it fetches the result. How result is searched in database? With the help of a key. Got it? So you are having a query, you give it to the database. This is your database, which is having key value pair. Understand? You gave a query, you are having a database which is having key value pair. So let us suppose key is 1, value is 10. Second key, value is 20. So according to the query, you need to get the value. And value can be accessed with the help of a key only. So query का dot product करना है key के साथ. This will give you attention score. Dot product. ये भी वेक्टर डॉट प्रोडक्ट करो तो दिस विल गिव यू स्केलर अटेंशन स्कोर. You have to normalize this attention score by dividing it by some value. जो आपने शेप लिया था वो 6 क्रॉस वो था 4 क्रॉस 1 होगा तो लेट अस टेक इट 4. So this got normalized. The values got normalized. Then you have to give it into sortmax activation function. Because there will be like many scores. Okay, ऐसी कई key value बनेगी. So sortmax activation you have to apply. And whatever be the result you are getting, you have to multiply it by the value. Then multiply with the value. Because I am having so many values. According to the sortmax will give you the probability. From here, which is having the highest probability, if it will be multiplied by the v, the answer will be maximum. Whoever will be the maximum, that will be selected. So यही मैं features के साथ कर रहा हूँ. I am going to select the relevant features from the data, from the image. जो मेरे काम के हों मैं उनको खींचना चाह रहा हूँ. अच्छा ये टास्क नहीं कर रहे थे क्या? कर रहे थे. I was doing feature extraction by convolution. That's what मैं कर रहा था काम. बट अब मैंने उसमें अटेंशन लगा दिया. अटेंशन. ओके. और अटेंशन लगाने के बाद this task is become much more fine. My overall goal is to attend those features which are highly contributing. ये अटेंड करना है मुझे को. ओके, विच आर रिलेटेड क्योंकि अटेंड करना है ना. आई नीड टू अटेंड, आई नीड टू फोकस. विच आर रिलेटेड. तो ऐसे मुझे फीचर मिल गए. देन ओके, दैट्स व्हाट आई हैव यूज्ड इन माय आर्किटेक्चर. आई हैव यूज्ड मल्टी हेड. मैं इसको वैसे और समझाऊंगा आपको, ऐसा नहीं है क्योंकि मेरा ये पूरा द थीम ऑफ दिस कंप्लीट this workshop is based upon architecture development, okay, and using attention mechanism. So here I'm using 8 heads. 8 heads means 8 attention mechanisms. 8 attention. A single attention is called as self attention. I'm using 8 heads. That means 8 self attention I'm using. Rest are the layers which I have already explained. You will add a noise to the data, you will perform the pooling, you will add a dense layer, then you can perform the normalization, then again you are adding the noise, then drop out for regularization, for reducing the overfitting. That's what you are doing. Main focus is here. You extracted the weights from the VGG16. Then you introduce attention mechanism, and then here you are adding more layers. That's what we do previously. वो करते ही थे तो when we make an architecture ना, ये तो I am not sure whether you use Gaussian noise or not. Okay, you might have used in your architectures when you are looking forward for novelty, तो ये आप कर रहे होगे, लेकिन attention use नहीं करा होगा आपने. Gaussian का भी I am not confirm whether you are using. अभी मैंने आपको दोनों बताया. And we have to incorporate such kind of layers in our architectures ahead also. Fine. Now, okay. Let me stop presenting. Let me stop recording.